Hey everyone, my name is Jared. I'm going to be talking about demystifying Shapeless. So kind of my inspiration for this talk is that for the summer, I'm a grad student at UCSB. For the summer I'm working at a Ruby shop and I'm writing a lot of Ruby and I'm really frustrated. And so I've been thinking about all these interesting ways about how I can get flexible typing to do crazy things. And so one of the main things that I've been struggling is I was porting from one version to another, and I was dealing with string encoding issues, and as a Shapeless programmer, I'm like, oh, I could have strings that statically know they're encoding. And so I started to go down this kind of rabbit hole, and I realized if you don't really understand the implementation techniques behind Shapeless, it's really hard for you to leverage these kinds of ideas as a day-to-day programmer. And so I wanted to kind of give a talk that was about exploring how is Shapeless kind of implemented, what were the ideas behind it, and how can you take this back into your normal day-to-day programming to get stronger static guarantees. So who am I? I'm currently working in Voca. We do telephony kind of stuff. We have custom telephony switch and a bunch of other cool things. It's kind of a fun technical challenge to work on. The Ruby part, I'm not a huge Ruby fan, but I also am a master's student at UCSB. I just finished my undergrad there. While there, I've done a bunch of different kinds of research. I've worked on a JIT compiler. I've worked on program fuzzing for Scala, actually. We can generate random Scala programs. It's pretty cool. On top of that, I've also taught the undergraduate, or helped TA the undergraduate programming languages class in Scala, so I've done a bunch of Scala there. Most of my research projects have been in Scala. I write a fair amount of it in my free time. I'm all over the place. As you might tell, I do all kinds of different things. I'm a really big Haskell programmer. I have been writing a ton of Idris, which doesn't have a logo as far as I know. I also have been writing a lot of Rust, and I also write a ton of Scala, and this is where I get to work, which is great. So what is Shapeless? For those of you who don't know, it's built with a lot of different things. At one point on the page, Miles built it as a framework for polytypic and generic programming, which might sound a little intimidating. Really what it is about is pushing the boundaries of what we can do at compile time, and providing a lot of interesting abstractions for you to do this. It tends to kind of go with a lot of the pure functional programming community, but I kind of think some of these ideas are a la carte. You can take them by themselves without having to import all of it in. And it's really become a playground for advanced typed FP in Scala. So it has a lot of features. This is just the main feature listing that Miles presents on the project page. So it's polymorphic function values, functions that can take different kinds of arguments. So for example, we can just peek ahead for a second. Something like this. So for example, I can declare this polymorphic function. It can take an integer. This is what I do when I get an integer. The second line is what I do when I get a string. The third line is when I get a tuple. And if, for example, if we call it on a list like this, we'll see for the integer we get one back. For the string, we get the length of the string. For the tuple, we get its size. And this becomes really flexible. So for about a year back, I was working on a prototype driver for RethinkDB, which is one of those NoSQL DBs that kind of popular on Hacker News or whatever. And I used Shapeless to actually, their query language is completely untyped. And I used Shapeless to get 3/4 of the way of emulating in Scala. So it's really flexible. So a bunch of other cool things. The main thing that a lot of things are built on are heterogeneous lists. You guys might have seen this. So this is a list where every element knows its type. So for example, if I get an HList back, like in the previous example, we can see I construct an HList on the second to last line. And then when I map over it, I get an HList as a result. And the type of this is actually int hnil. We'll talk a little bit more about that as we go on. And there's tons and tons of other features. Honestly, some of these by themselves are probably a 40-minute talk. So I'm going to just kind of go to high level. And again, kind of focus on extracting the wisdom from the implementation of Shapeless. So it was kind of inspired by a lot of things. In the Haskell community, there's this idea of scrap your boilerplate. So back in about 2003, I want to say there was a paper by Ralph Lamel and Simon Payton-Jones, I believe, on doing generic programming over many different kinds of data types. So for example, they wanted to implement something like a generic map or a generic fold function and have it be implementable for any data type. So their original thing required very little boilerplate. It required you to do one little declaration of a type class. If not, they also provided a tool that would automatically generate that stuff for you. Over time, it's become more advanced. They actually released a series of papers. But with Scala macros and a lot of stuff that Miles has been doing, this has become really boilerplate free in Scala. There's also more inspiration from things like generic deriving. So this is for example, there's a simple type class that the Scala Z people use called show, which prints a string representation of your type. For example, you can have it automatically derive something like that for you, but you can also have it derive equality and so on and so forth. Or like Adalbert was talking about yesterday, you can have it derive a monoid instance. You can do all kinds of cool things. And then a lot of the inspiration has been taken from dependently typed languages, which are usually kind of thought of as these academic, esoteric things. But there's actually a lot of cool ideas, even if you're not programming that language, that can be imported back. So the main thing, again, I was talking about is static reasoning, and this is really what I'm interested in. if anything, my research experience as doing programming languages stuff has taught me that this is really, really powerful. And then back in the engineering world, it's really nice to just say something holds and know it holds instead of reasoning about, all right, what are the different failure modes? And this is something that I've really, why kind of my experience writing Ruby has kind of instructed some of this talk, is that there's so many crazy things that can go wrong because everything happens at runtime. You can redefine methods, you can do all kinds of insanity. But I want to go to the other end and say, how much of this can we fix at compile time and have the compiler give us an error message? Because it's much better to have the compiler tell me that I'm an idiot up front than me to like crash a server in the middle of the night and get hit on pager duty or whatever. So the way Shapeless works, almost everything's happening at compile time. You pay a minor cost of passing around these proof terms that we'll talk about constructing, and also you pay it in compile time because the implicit selection takes a while. So I just want to show some more examples a little bit. So this is something that I had helped Adalbert with a few weeks ago probably, where he had a list of any things and he wanted to come up with a Typesafe Cast and just cast it into a case class. And if the cast works, you'll get an option back that's either the value you wanted or nothing. So in this case, what we do here is you give me a list. If it's castable, I can give you a point back or a not, and you can do this for an arbitrary case class. It requires no boilerplate. So if you import Shapeless and you grab this snippet of code right here, you can do this. Just hand me a list, and the list typing could also be different. But list of any just here to demonstrate that you don't actually need the typing information right there. There's other things like Joni Freeman has been working on type SQL. So for example, that string is actually checked at compile time. It produces a chunk of code that then is a polymorphic function that we can call. So for example, we can run the query. That's what the calling of Q does. We run the query, we can map over it, and we can get the age, for example. So in this case, we got all the ages from the query that we ran, and we get 36 and 14. You can check it out here. There's been quite a bit of cool work done, and I encourage people to go look at it. One thing I want to touch on kind of before we continue is a lot of these ideas are pulling from these dependently typed languages. The really only big takeaway is that there's this relaxation of the phase distinction. So if you're a Java programmer, for example, or a Scala programmer, you're used to types and values living in very different worlds. They're not allowed to mix in any way. And dependently typed languages are really about easing this and saying, hey, my types can now talk about values. Also, I can do computation at type checking time. So if you go to Idris, for example, you can do things like run an arbitrary function in your type signature, which is kind of cool. Obviously, Scala doesn't give us quite as much flexibility, but a lot of these things that are built as type level programming are actually just kind of stealing ideas from dependently typed languages and bringing them over the fence. So to kind of illustrate this distinction that I'm talking about, you could, for example, look at something like this vec type. So what we really want to write is, imagine if we're in this dependently typed version of Scala, we could ask for the constructor for a vector to take a nat, which is its size. So we're using natural numbers here because they're always greater than 0, or 0 or above. And we also take a type and we return a type. So for example, you could construct a vector of size 1 that contains a single integer, and it would be, vect1 int. But in Scala, if we wanted to write, like this is our pseudo Scala right here on the third line, if we look at that, for example, those are both types. What we're really writing is that this trait is parameterized by a type, and we get a type back. And so really a lot of what Shapeless does and a lot of these techniques is about how do we get around this? How do we exploit the language in a way for us to write something like the ideal, but we can't, so how do we estimate? So one of the important things is a bunch of people bandy or kind of talk about types as logic. This is only really useful to us as a high-level understanding. We could all, again, give a 40-minute talk on the implications of this. In the theoretical PL community, there's a lot of research done on this every year. People are turning a lot of new interesting work in this area. But really, the main idea is that if you view your type system as a logical framework, and we can just simply map one-to-one types to propositions and programs to proofs. And you might not follow with me yet, but we'll explain it by the end of the talk. But with this caveat, a lot of times when people hear me say the word proof, they think I'm talking about something interesting, right? Like every proof has to be interesting. But for example, if I ask for a proof of integer, I can produce you an integer, right? That's proof of an integer. I just want one integer. They're not always very interesting things. So that's something to keep in mind. So if we want to emulate some of these ideas, which is kind of my goal, because again, I think it's actually very much engineering motivated of I want this thing to fail before the compiler finishes running. We need to get around this phase distinction. So the thing is, what we really want to do is we want all of our values to also have a type level representation so we can put them in the type. And we'll kind of get into that in the next slide. But essentially, it's this third line, right? Is that I want to be able to use 0 as both a value here, and I want to be able to use 0 in the type and say, hey, this vector has no elements in it. So we're going to start with natural numbers because this is like the simplest thing. It might sound kind of contrived, but you actually need them all over the place, right? Like if you want to do indexing, numeric constraints like, hey, I want the size to be less than n, all kinds of things like this. The traditional natural representation, which comes from math, is kind of an idea of a 0 element and a successor function, and you apply the successor n number of times to reach the nth nat. So if we apply it once, we get 1. If we apply it twice, we get 2. If we apply it 3 times, we get 3, and so on and so forth. And we're going to what we're going to do is we're going to concentrate on the value level. We're going to look at a value level representation. So like typical case class, everything, something that everyone should be familiar with. Then we're going to say, all right, mechanically, how do we take this and transform it so that we can use it in this type level style and get a lot of benefits? So for the value level, we can take something really simple like this. So we have a value representing a natural number. We declare a sealed trait. We have a case object that represents 0. We have a case class that represents successor. It takes a natural number and is also a natural number itself. So this is the function we talked about. If I apply suck to 0, I get 1, so on and so forth. You could provide an implicit conversion that converts integers to this if you really want it to syntactically be nice. But the real question is, how do we go from that initial idea of, all right, we have this value that looks like a natural number, and move it to the type level. So the problem really, right, is that if I give you a value as a nat and you want to use some type information about it, I have no way to like compute the type and stick it in a trait, for example, or in my method declaration. So we're going to first cover a few prerequisites. So this stuff kind of stretches, maybe, I don't know if people think these are the esoteric language features, they might be. It kind of stretches in that direction. So we're going to cover all of them so that everyone has a good idea of what we're using and why these things are useful. We'll cover them first, and then as I go through my explanation afterwards, I'm going to try to highlight where each of these fit in and why they're useful. So implicits, everyone knows, loves, or hates, I'm sure. So really simple, the way we're going to use them is they allow us to just pretty much demand something and have our demand satisfied. So in this case, we need something of type int, and we're going to go look in the implicit scope at some point and pluck it down. And we're going to use this style all over the place. And I really like to think about it again as like obligation and fulfillment, right? Someone owes me an integer, please provide it to me. And I think this is useful because as we construct these types that represent proofs, it's really going to be say, give me proof of this thing, and I can do the thing that I'm implementing in my method. So type members are one of the things that we first want to cover. So type members are useful because it allows us to put some type information in the value. And we'll see that as we're talking about merging the value in the type level, it's really important that our value has some information about its type. So for example, this is something contrived. We have a user. We want to maybe hide the type of the email. We put it on here. They also have an email. The important thing when we construct these things, we also need to set the type member because it's part of the construction of the object. And that should be good. The interesting thing about this, though, obviously, is that the type is existential, and what this means essentially is that it's hidden, it's abstract, right? So when I get any user on this last line right here, the type of email is hidden to me because it is a type member, right? All I know it is some type, but unless you use structural refinement, which we're going to talk about in a slide, there's no way for you to see it. So we can also make use of structural refinement types. So this is about refining them, taking a type like this and exposing this piece of this information right here. So another kind of simple example is, assume we have some data store and we want to have some database that backs it. And we want to actually hide that information from most of the users. But every once in a while, we might want to express that we only take a certain kind or that we only work on something that we know where the database type is. So in this case, we can declare, if we're going to use Postgres, the type of DB must be Postgres. And Postgres in the last release just added binary JSON, for example. Let's say no other data store has it for the sake of the example. We say, all right, writing a binary blob of JSON requires it to be Postgres. And as we can see, this kind of thing will work and this thing will fail because it won't have enough information to say, all right, I can prove that this data store where I don't set the type actually has Postgres. And so this is going to come into play. The other important thing with this is it's subtyping. When we do a subtyping here is, if we have this unrefined trait at the top, and we refine it with some piece of information, in this case we say part of the type is actually the fact that its member T is string, This is actually a subtype, and this is for those of you who are not familiar with it, this is that weird implicit operator that will only return an implicit. These two things are actually a subtype. So in this case, this implicit returns us a value, and refined is a subtype of unrefined. So the subtyping rule is important really for this reason, because we're going to see on the, let's peek ahead for 1 second. So here is our natural level representation, right? So this might look a little weird, but what we do is we take a nat, and we know that, all right, we have some base class. All we do is reflect its type as part of its value, like as part of the value. So now every single natural number also has a member called n that contains the type of itself. And in this case, 0 is the base case. This is equivalent to the 0 that we saw a few slides below that was the case object. And we simply extend it, and we set its number to 0 itself, right? That makes sense. And then successor is the same thing, except instead of operating at the value level, it operates at the type level. So we have a successor. We say any previous nat, right? Can be any nat. Will provide you that its type representation here is the next number after it. And so if I do suck of 0, it's equal to 1, and we can see that like right here, for example. So we can imagine, and Miles does this in Shapeless actually, except he's gotten a little bit more clever about it. It has a macro. So if you try to do something like turn -1 into a nat, it will complain and throw its hands up in the air. But the nice thing is here is we have a nat. We can actually grab a type out of it here with n. And so in this case, that would be equivalent to suck 0, which is 1 for all intents and purposes. And the reason why we want to use these bounds is important is that if we just do something like this, when we start looking for implicits, every single natural number will give us the same thing back for this. But if we use the bound instead, we allow it to be some subtype. So for example, because 0 is a distinct type, and suck of 0 is a distinct type, and suck of 0 is a distinct type, and so on and so forth, we can actually find distinct proofs for each one of these types. So if we have a proof, for example, that says 0 is less than any number that's a successor, and we go to look for that, we will select it correctly, versus if we just looked for nats, it would totally fall apart and wouldn't work. So the main thing, though, is now that we have looked at the type level representation, it might not be super clear yet. I think once we look at how to implement a proof on top of it, it will be. We can look at like this value level. So if we go back and rewind to the value level, and we look at less than like this, we write a simple algorithm right like this. We match, which I might have inverted. I did. Writing too much Rust. So we match. We do the case. The simple case obviously is 0, and some successor is always true, right? 0 is less than any number that is not 0. This case right here, we just subtract two things. We subtract both numbers by 1, and we continue recursively. And then here, we just return false. And the reason we're doing this recursively is this is kind of how all the implicit selection is going to have to work in a minute. And it's easier to do it that way. So what we really want to do is translate this piece of code, and I think this is a relatively mechanical process. So in the value level, we're returning a Boolean, right? Like at runtime, we want some answer about whether this thing is true or not. But really what we want to do at compile time is we want to provide some implicit if the relationship holds, or not provide the implicit. And why this is interesting is the compiler will halt when it can't find an implicit, right? So if the implicit is not available, or there's no way to manifest said implicit, the compilation will fail. And so what we first need to do is we need to translate the thing we want to prove, and we can use prove in a loose sense here. In this case, we just want to demonstrate a relationship between two numbers. So in this case, for any number n and any number m, this will represent a relationship that they're less than each other. So if you have one of these objects, someone has proved to you that n is less than m. And so now you might ask, how do we do this? So we have the trait up top that we just looked at, just to keep it in scope. And you can see that before we had, in the value level algorithm, and I'm going to step back to that for a second. In the value level algorithm, we have 3 cases, right? We have kind of this base case up here where we terminate. We have the recursive case here, and then we have the fall through. So the cool thing is the fall through disappears because there is no, the failure is there is no implicit, right? We can't provide you a proof. So the nice thing is we eliminate the fall through, and then we just take these 2 cases and we're going to mechanically translate them into implicits. So the cool thing here is that for the base case, right, we say for any number m, which we need to do this little bit of a trick right here, any number m I'll provide you a proof that the successor of that number is greater than 0. And the reason why we need to do this is to exclude 0. So if we didn't do that, if we just said, all right, give me any number m, and I'll prove it for you, prove that it's 0, that doesn't work, right? If m can be 0, then I can provide you a proof of 0 less than 0, which is totally not true. So the thing is, we do this little trick right here to ensure that we're always providing we're always correct here. And this is something kind of, I think, important to draw attention to is when you're doing this kind of stuff, doing these kind of things, it's hard to make mistakes, but you can still make mistakes, right? Like you can encode a proof that is not what you really want to say and then satisfy it. So a lot of times when people talk about this stuff, it seems immune to these kind of failures, but you're still totally have the specification problem, right? You need to be able to specify what you want to say, even if you're able to say it. And then so for the recursive case, it's pretty easy as well. So all we do is say, for any n and m, find a proof that n is less than m. So this was like doing the recursive call before, except it happens at the implicit level. And then we construct a proof that the successor of n and the successor of m are less than each other. Because obviously, if we take 0 and 1, for example, and we add 1 to both, they're still less than each other. If we take 0 and 50 and we add 1 to both, they're still less than each other. And so that should kind of be intuitively true. Then here's the final linking piece. And I'm just returning true because we're not actually doing anything of note here. But you can take values. So look, I take a value representation of a nat and a value representation of a nat. And then I just simply ask for proof that their type, that the type members they have that relationship. And so this is how we tie the knot on moving. So now we don't need the value level representation at all. We now have a representation that exists both at the value level and the type level. And when we need to talk about the types, we simply just reflect them from the value into the type signature here. So we can move on to HList, which is like the bread and butter of Shapeless. And I thought it definitely worth talking about a little bit, which is also really simple. So most of the complexity in Shapeless is around encoding these different proofs of like, hey, can I take 4 elements off the front? Can I index into the 5th element of a list that, like, in that case, I need to prove the list is at least 5 elements long, otherwise I can't do that. And things like that, or head, and which we're going to look at in a second. So we start again, same kind of pattern, sealed trait, base class. And we're going to use this again because we want those bounds everywhere to do selection of subtype. Then we're going to declare a case class. And the cool thing about the HList is actually that it's covariant. So if you have a list of any, you can pass a list of int, so on and so forth, similar to collections. And so the nice thing here is that we simply just declare that there's some head type, there's some tail type, and then see, we use the bound again to say it can be any HList. So this is important because with the subtyping relationship is t can be the precise type. So for example, if the end of the list is a single integer followed by nil, we recover all of that information when we construct it. First, we could ostensibly throw it away, right? If we only ask for t to be an HList, right, like if we remove that type parameter and just say tails an HList, we would lose all that extra information. So the nice thing is that this bound allows us to recover some precision here, and then we can put the precision in when we construct it. So in the constructor, we only take something that types to H, and we only take something that types to T, and then we produce an HList as well. And then we do this little trick right down here, and this is a trick I did earlier in the slides, but case objects don't declare a new type. So this is, again, kind of in line of we create a type representation of HNil, and then we create a value level representation of HNil so that we can use it both at the type and the value level. And if you think back to, or I have an example right here, if you see right here, the type is int string HNil, and you can get away with this because types with operator names can be, or actually all types can be used infix. So that's really all that the trick is here. You could provide it a more verbose name if you liked. But you see HNil exists both on this side and this side. And that's because we created a type HNil. We also created a value HNil. All right. So here's a really, really simple proof on HList, right? I want to prove that there's at least a single element, right? That there's one con cell in the list. So this is equivalent to statically asserting that my list has one element. So the thing here is when I encode a proof object, oftentimes what I'll do is I'll insert the functionality directly into the object. So I add these type fields, and we'll see why these are important on the next slide. And then I tell you, I say, hey, if I do provide you this proof object, it will have the functionality to call head, and it will have the functionality to call tail, and they'll be properly typed. So the cool thing is then this looks really, really hairy, but most of this is super mechanical transformation. So if we look at the top, I've omitted some of the code that is in the actual implementation from Shapeless. There's this aux type alias, you can mostly ignore this. This is just a convenient way of writing out that long structural type on the second line. So instead of writing out is hcons L type H equals something type T equals T every time, I can just write this little shorthand, is hcon.aux and then provide the type parameters, and it looks a little bit cleaner. So the thing here is that I just want to provide there's only one case, right? There's the case where I have at least one element, and I don't care about any other cases. So you can look that, again, we take some parameters, and this is to allow the type inference. We're kind of almost programming the type inferencer in this way. We're getting it to solve some unification. So in this case, when we have head and tail, we declare them. We're hoping they're going to get solved. We say, if someone asks for a proof of head const onto tails, or onto tail, what will happen is those variables will be solved. All this other stuff will flow. So if I ask for a proof of int hnil, head will be solved to int, hnil will be solved to tail, or tail will be solved to hnil, and then, oh, there's misindentation. But then both of these variables will be set to that. So in this case, head will be int, and I will then provide a method that shows you how to get an int from that list. Tail will be hnil, and hnil is an HList, so this will work out just fine. And I'll provide you with a way to return that. And we notice that we take the full type, so this takes int hnil, and this takes int hnil. And the nice thing there is that then on the other side, so this is the messy proof implementer side, which you can actually mostly ignore most of the time if you know what the proof relationship is. So in this case, this is the actual method definition on HList, and it's really simple. If I want to call head, I just ask for a piece of proof, and then we use a feature that I mentioned earlier of path-dependent types. So path-dependent types sound complicated, but it's a very simple form of dependent types in Scala that allow types happening on the result side to be accessed from values. So in this case, I get T from C, and we notice again, we have a type now depending on a value. So in this case, the return type is determined by the implicit we pick. So if I find a proof in this case that I can actually pull the int off the front of our list, then I will return you an int, even though it doesn't say that right there, and I will invoke the functionality on the list and get it back. So you could be totally unaware of how hcons is implemented, and you could ask for this chunk of proof and have it manifested to you. And that kind of goes back to one of my main points with Shapeless, is that most of these proof objects are black boxes, and this is something that I missed when I first started programming in Shapeless. I found it really complicated. What I realized is that anytime you start to write generic code, if it can't be completely statically determined, you need to push it up and say, I need a proof obligation before I can run this code. And to kind of illustrate this is, for example, generic. So generic has had a few different implementations in Shapeless. The current one is an implicit materialization macro, which is really complicated. I don't actually know anything about how it's implemented, but I can totally use the functionality of generic unbeknownst, because that's the proof part of it is pretty much a black box to me. So in this case, I ask for all of these objects, all the companion objects have an apply method that takes a single type argument that will give you back the generic instance. So in this case, if I want a generic point, I can just get a generic instance for a point by asking for it right there. So we get the generic, and generic is this cool thing that allows you to provides a conversion between product types, so like case classes, tuples, all that kind of stuff, into an HList representation. So what's cool about this is, given the HList representation, you can do all kinds of generic programming things. So you could write serializers on top of this and do a bunch of other pretty cool generic programming techniques. And Miles actually implements a lot of this in Shapeless, so if you're interested, go look there. But you can see then, I annotate the type here to be kind of clear. We're going to get an int and an hnil when we go from, and then we're going to go back to, and we're going to compare equality, and it should be identical. So this provides transformation one way or another, and it's pretty cool. So for example, one of the things, if I have time, is I implemented like a very small chunk of like automatic like SQL deriving. So like you could just say, hey, I want a create statement for user, and it will just spit out SQL for you. And it's done all generically. So any case class works. And it's just like the as example that I showed a little bit earlier about the casting. Again, it's completely generic. You just provide an arbitrary case class and it happens. So applying it, this might have seemed more esoteric, but again, the idea is to get kind of the wisdom of it. Is that we can build a bunch of cool things. So some of the stuff that I played with and other people played with is type SQL, type JSON schema. So this static string encoding is what I've been working on lately. I know Spray uses it in their routing layer somewhere, and a bunch of other people do. So as we're getting closer to time, I think we'll work on this encoding example. So this is something I hacked up in the last few days, as I thought it was really a valuable insight. I don't actually use any Shapeless in the implementation of this. There's a link to it at the end of my presentation. But I declare a bunch of encoding types, and this is pretty much boilerplate. Like I declared UTF-8 and ASCII and ISO 8859 or whatever Latin one is. And I declare an encoded string, and we leave the implementation out because it's really not that important. Store it as a byte array or something like that and convert to and from. And then I also wrote this macro, which I'm putting here just for completion's sake. And this will statically assert the encoding of a string. So for example, if you say, hey, this string is ASCII, and then you put UTF-8 characters, it won't compile, which is really, really powerful. Again, I don't know how many of you have had to deal with really annoying encoding issues, but if you have ever dealt with encoding issues, getting a runtime error somewhere when you try to concatenate two strings together or something like that they can't be transcoded is incredibly frustrating, especially when most of this information is known statically, or if not, can be recovered. So again, I'm just going to show you the proof objects because again, the implementations don't actually really matter that much to us. So in this case, I declare a transcoding. And so I start with some initial encoding. I'm going to have some result encoding. And then I provide a method to transform from the initial one to the result one. So you can come up with some simple like proofs in your head if you think about this. Something that satisfies this is obviously the identity, right? If I take something in UTF-8, I can always give it back to you in UTF-8. But the reason why this is a useful building block is that I can start to talk about higher level operations based on this small snippet of code. So assuming that someone has given me a transcoding, oh, and I think my code got clipped. This is slightly incorrect, sorry. There's a missing implicit here. And so the main idea is that if I take a prefix and a suffix and a result, normally I would take these two things as arguments, and then I should also have an implicit argument, and I can pull this snippet of code up in a second. I should have an implicit argument that asks for a transcoding from both the prefix encoding to the result, and both from the suffix encoding to the result. So ideally is, if I want to concatenate two strings at compile time, when you ask me to concatenate two strings, I'm going to search to say, can I go from the encoding of the first thing and the encoding of the second thing to a common encoding, and if I can add them together. And so this is really, really powerful because now you've eliminated a whole class of bugs and things that cannot ever be merged, like binary and UTF-8, for example. You will not be able to do that. And then on the client side, if I want to demand this proof, I simply just do this thing. So I say, this is actually the implementation of CanCat, like the one you would type in. And this one says, hey, there's two encodings. I'm going to take the two encoded strings. You're going to give me proof that I can cat them. And if so, I'm just going to invoke that functionality. And again, this shows how simple it is to depend on these things while being ignorant of their implementation. And so I think we still have a few more minutes. So I have another extended example. So one of the things that when I was working on the SQL stuff is proving that one HList is a subset of another HList. And you might ask, all right, is this a useful proof? But for example, Miles has now come up with this cool thing of Singleton Types. So for example, this ID field now has a unique type. So ID, the string, can be typed different than the field, bogus field, or age, or whatever. And this is powerful because then if I can take like this list of updates, for example, convert them into a list with precise typing on all of them, and then I can ask if they're a subtype of the ones that exist. So for example, user, if we see above, has 5 fields. If I ask for that thing to be converted into a representation that is the keys and the values as pairs, and I ask if this set that I want to update are a subset of that, I can now statically assert whether I'm allowed to do an update, which is kind of cool. If I throw in a bogus field in there, for example, the compiler will reject me and not let me pass. So we look at drill down into the update example. This is what I was talking about. And we can then look at the proof. So again, we declare a relationship on types. In this case, we want one thing to be a, one thing is our subsequence, one thing is our supersequence, or like encompassing sequence. And then we encode a set of proofs. This is a low priority one where we essentially skip an element, and I'm running short on time, so I think I'm just going to fast forward. So this is like the main one of interest. But mostly, again, I'm just doing the programming. Instead of matching at the type level, I'm programming the unifier to get it to do kind of things that I want. So in this case, I need, I skipped the slide ahead. So this is a simple case, right? When I want to provide a proof that H0 is a subset of H0, right? This is really dumb. If you ask me a proof of that, I can simply just provide you one. right? The more complicated one is this one where I'm actually going to do computation at this level. Here, for example, I take, I want to prove that H and SH are equal. Then I need a proof that T is a subsequence of ST. And then then if so, I provide you a proof that the whole list is in fact a subsequence of the combined list. And it again really looks, it's hard to read this style, but it's pretty mechanical. Once you get used to it, it's easy to transform. And also you get a lot of power. So here's a few links where all my code is, and on the GitHub repository, I think I've pushed everything. I'll probably be polishing some of the code up over the next few days. Feel free to bug me on Twitter or email or whatever. I'm always happy to help on this kind of stuff. And then acknowledgements, I just want to thank Miles, obviously, for working on Shapeless. It's pretty cool. It's been a fun, interesting way of seeing what's possible in Scala. My lab for hosting a practice talk. And then Adelbert and Pete for giving me some notes on my slides. And then questions.